Starting the recording. All right, so I want to continue where we left off on Wednesday, where we were talking about building up to a derivative. Now, this example here, again, I showed the limit definition, but the nice thing is we have some rules that we can follow from the patterns that come about with this. Okay, so if you look at this particular problem here, and we wanted to differentiate it, so get to that derivative of g of x, we could use the limit as h approaches 0 of g of x plus h minus g of x all over h. That is one option. All right. While we work with this is going to be something that you want to see that it can get a little tedious, right? So we don't want to have to do this all the time, especially when a function has a little bit more going on. So that's something that we're going to work towards some of the rules today, get them in place. Okay. But remember here, if you ever had to do, oh, that did not work. If you ever have to go through this process of the limit definition, just remember it's about simplifying. So like first finding g of x plus h. So that'd be 9 minus x plus h squared, which would be 9 minus x squared minus 2xh minus h squared. Okay, the one thing I would say there, if you ever wanted to do that on your own, be careful with the negative here because you have to square first and then distribute the negative, which is why each of these becomes negative. When you go to the difference quotient side of things, so we bring it back to that limit as h approaches 0, remember here that this is nice because when I go to start comparing all of these things with the original function in the subtraction, our terms that do not have h should be dropping out. So we had a positive 9 and negative 9. We had, a negative x squared and a positive x squared. Okay. The one thing I did highlight, though, is the terms left over should have h on them since we're working the polynomial. And this would simplify down then to the limit as h approaches 0 of negative 2x minus h, which at that point we could do a direct substitution. Okay. We don't need the graph because, hey, h, if it approaches 0, it's going to be 0. So what we see here is this would just give us negative 2x. Okay. Now, if you remember the first time I did that, I pointed out that that negative 2 isn't made up. There was a negative in front of the x squared. There was an exponent of 2, so that 2 didn't just come from nowhere. It's a part of the problem, and these patterns are what we want to focus on today. All right. Now, keep in mind what I added then is as we look at this instantaneous rate of change, this is going to be our derivative function. All right. So this piece here is what we're going to call our derivative function. I know I'm going through this quickly, right? But it's not about the limit. I'm just showing you like, hey, this is where it's coming from, but this is where we're trying to get to. So there's any questions I can clear up with that? All right. So as we move into the next phase of this, we're going to be able to talk about dealing with functions and their derivative. So the first thing we want to look at here is going to be the power. Okay, as we looked at this problem before us, we dealt with x squared, and we can take that pattern to help us move forward. So if I take everything away and it's just x squared and we go through that whole process we just did, we would get 2x. Right, but it doesn't just work for x squared, it works for any exponent that's a real number. Okay, so that's what you're going to see with the power rule. But be careful here to see that even though we didn't write what was going on, what happens up here is this was 2 and we took 1 away. So when you do that, it becomes x to the first, which is just x. That's going to be what we want to bring into the power rule, that we're changing the exponent, but that exponent that was there becomes the coefficient. So as you deal with this here, the derivative of x to the 7th, its power rule would say, hey, let's bring that 7 down in front. I'm going to keep the x as the base, but the exponent, I want to subtract 1 away from that. So that would give me that this thing equals 7x to the 6th. Now, with that in place, we could also do it for any real number, as you see here. So it didn't have to be a whole number. It could have been a rational number. It could have been an irrational number. Okay. We could also do it with negative numbers. Now, one thing to be careful of is just make sure you remember that when you see x to the negative 3, this is the same as 1 over x cubed. So there are some things that we'll have to keep an eye out for, like we kind of talked about, like, hey, there's some continuity concerns there because x can't be 0. But when those things come up, we'll deal with them. All right. I hope that from our conversation, you kind of picked up on that. Like, hey, when we get to that situation where we need to deal with it, that's when we'll make sure to talk about it. Okay. As you deal with this derivative, though, take the same approach. When differentiating x to the negative 3, we would say, hey, this is going to be negative 3 times x, and then we're going to subtract 1 from the exponent. So instead of negative 3, now it's negative 4. Any questions, concerns there? All right. So the next thing then, because that covered up, if we just look back at our first function, that covered this term. So what about constant terms, right? So that's our next one. Right. Now keep in mind, we're still talking about average rate of change, right? So when you see the derivative of a constant term, if I draw the graph of a constant function, so like y equals 3, it would look something like this. Well, it doesn't matter what 2 points you pick. As you go from left to right, it doesn't go up or down at all. So the average rate of change will always be 0. So this right here should not come to a surprise. Now, the reason we need to make sure we have this in place is because, again, look at our first function, right? We had a constant term, right? So we're going to have to talk about how to handle that as we go through here. So make sure you see here that I just picked it for the example e squared. Make sure you remember e is a constant value. Don't need to look that up on a calculator as long as you know it's constant. Hey, the derivative of this is 0. It doesn't matter the constant value. It could be a negative 50. It's going to be 0. Now here on the other one, I have pi. All right, if you remember, most time we use 3.14 for pi. Not that we'll use it a lot in this course, but again, it's a constant value, so it would equal 0. Any questions or concerns with that one?
Yeah, one more time. How do you know it's going to be a constant?
It's a constant value. There's no variable involved.
Got
That's the key. If I don't see a variable, that's why, again, I picked to put e squared there, though, to make sure to remind you, like, e has a value. E itself is not a variable, okay? Like going back over here, we had an x squared term, so that's a variable term. And then the 9 here has no variable on it. So no matter what I do, that's always going to be 9. So that's why we call it a constant term. Now, there will be times where we have just, as we see here, like this situation. But what we're going to run into is that, hey, we're usually going to be working with functions, which is why I keep going back to this example, right? If you remember in class the other day, we also went over this example as well. But this one, remember, I just did the limit definition of the derivative. Other questions? All right, so this next one here, I wanted to kind of walk through what happens when we get to those terms. All right, so I picked a function here where it's 2x minus 5. Okay, what you're going to find is we have two things as far as dealing with a coefficient and dealing with terms that helps us out. So rules of derivatives is, hey, I can break this up. If I have a constant multiple, that's what you're seeing here, is if you have a coefficient multiplied by something. So if it was like, say, 2 times x squared minus 3 is kind of what they're saying here. This is your function. This is just a coefficient. It's a constant value being multiplied, right? What you see here is you could just bring that to the outside of your derivative and focus on this part, okay? Now, as far as the sum and difference, what they're showing here is if you have multiple terms involved or different functions, you can take the derivative of each one of those terms or functions that are being added or subtracted separately, okay? Similar to kind of what we see with the distributive property. So that's what I did here, okay? I have 2x minus 5. So the first thing we could do is break up the derivative to focus on the 2x and the 5 separately. Then over here with this piece, as you can see, since we had the 2 being multiplied the x, I can bring the 2 outside, so my derivative focuses just on the x itself, and we still have the 5 there. All right, going down to this next step here, though, the derivative of 5, since it's a constant term, is 0. X has an exponent of 1, right? It's a linear term, so make sure you see here that what I'm saying is if you have x, another way to write that is over 1, which you don't need to do this all the time. I'm just making sure we have a clear understanding of what we're doing. So I use that power rule that we just looked at for that piece here. I brought the exponent of 1 out front, but then remember, when you subtract 1 from 1, you get 0. And that brings up another rule that's important. Anything to the 0 power is just 1. So what we see here is that would just give us 2 times 1 minus 0, which is where the 2 comes from. Any questions or concerns with that one there? All right. One thing I would say then, this is definitely a place where you're going to need to practice the rules. You need to make sure you go on the homework and work work out the homework, but if needed, work out more. Go to the e-text. Let me know. We can pull up another free textbook that has plenty of examples in it too. All right. It's definitely important that we're practicing as much as you need to make sure you're comfortable with these rules. Now, there's going to be more rules that we add, but I felt like focusing on these was a good place to start. Right? I can give you this function, say, hey, let's differentiate it now. Okay. Make sure you see here, taking this and differentiating it, we can focus on each of the terms separately as we just talked. Now, you're not going to have to write this out in this form every single time, okay? So make sure you keep in mind, I'm just making sure to show you, hey, we're focusing on each term. You don't have to write this step out every single time you take a derivative. What's helpful about it is you're saying, okay, I'm taking a term at a time. So as I look at this term, it's going to be 2 times what I get from the power rule. So I can bring the 3 out front. I keep the x alone, but remember, then we need to subtract 1 from the exponent. The next one is the same thing, but this time it's 5 times that. But remember, when you have just x or a linear term, you're going to get just 1 from that. Or in the end, the coefficients, all that's left. With the last term, though, 9 is a constant value. The derivative of a constant value will always be 0. With that said, then what I have here at the bottom is my derivative function of g. Just make sure to multiply it back together, and you have what you were looking for. Any questions, concerns with that one? All right, so let's do another one then. Go ahead and work these two out. I want you to find the derivative function using the power rule, the sum and difference of derivatives, as well as what happens when we have derivative of a constant. Give you a couple minutes to try these out. By the way, if you haven't put your name in the chat, please put your first and last name in there so I can get you for the attendance. So to start working these out now, the one thing I hope that you take from the rules is that to take it first and foremost, one term at a time as we go through here. So this first one, since we have a real number as an exponent and the variable is our base, that's where we're going to say, hey, this is a great time to use our power rule. It's very important to see that our base of this exponent is the x, though. That's why we're allowed to use the power rule. It's whenever our variable is the base and we have a real number as an exponent. With that said, then you'll have here 7 times 2, and then it's just x. Okay. If you wanted to, you could just write that as 14x. But just make sure to see the 2 is coming from our exponent. The next term, though, is going to be just minus 3. Again, the derivative of a linear term, x, would give us just 1. So 3 times 1 would be just a 3. Lastly, you would have the derivative of a constant term. So just remember at that constant term, hey, the derivative of a constant value is 0. So this would actually end up being all that we need here. One thing that you'll start to see is patterns-wise, if you take a derivative of a quadratic function, the result should be a linear function. Any questions with that one? All right, so the next one then, we're dealing with a larger exponent, but that doesn't change anything. Okay, just I picked a higher power for our polynomial. It has degree 10 now rather than degree 2. Just be careful as you go through that you're keeping the coefficient where it is and you're multiplying by whatever the exponent was, and then only subtract by 1. Okay. So this next one will do the same thing. Negative 6 times 4x and then cubed plus 5 times 2x. Now the last one's special because we don't want to put the 1 there, right? Yeah, 2 minus 1 is 1, but anything to the first power is itself. Anything to the 0 power is 1. Those are some special cases we want to make sure we're careful with when writing out our work. Now, as I showed on the previous one, though, if you're comfortable doing the multiplication at the same time, you could have just wrote negative 20x to the 9th minus 24x cubed plus 10x. Any questions, concerns there? All right. Now, as I mentioned, there's going to be other rules we deal with, but there's one function that we kind of walk through that's rational that we don't need more rules for yet. So let's look at that real quick before we finish up. I say we have this rational function here. We want to differentiate it. As we deal with the rules of differentiation, we're going to be able to talk about what happens when we have product rule situations. So what if I gave us something like 2x minus 3 times x plus 4, okay? This is a quotient situation, right? We have a fraction involved. Well, one way to deal with either of these situations is let's try to simplify first to get it to look like what we have over here, based on terms rather than division or multiplication. Now, the nice thing about rational functions, sometimes, not all the time, right? This one here, it's just x squared in the denominator. You can simplify it by writing that as individual terms with that denominator on each of them. What's going to happen there is this is going to make the function a little bit nicer for differentiating. All right, it's not a normal way that we write stuff, but like I said, our purpose here is let's go find or differentiate the function that we have. So find the derivative of f of x. What you'll see here, the nice thing about rewriting it this way is I can go through each term now and deal with that. Now, one thing I will say, if you're having trouble with this, go back to what I said at the beginning. Another way to write that is 2x minus 3 plus 5, and then x with the negative 2 as an exponent. Okay, so negative exponents will be helpful here. So that's why we like to write it this way, is because, hey, once I write this as a negative exponent, I can go back and say I could treat it just like I did these two. All right, so focusing on what we have here, hey, the derivative of this first term would just be 2. The second term is a constant, so that is 0. And then lastly, we would say, hey, 5 times, then we're going to bring the negative 2 to the front, but make sure you're subtracting 1. So the negative 2 becomes a negative 3. This would give us 2 minus 10x to the negative 3, or if you want to write it back the way it was before. Okay. I personally would say you could leave it this way, or you could put it that way. Either of those would be fine. Now, be careful to read problems when you're doing on the homework side of things, right? When you're doing homework, if it says no negative exponents, make sure you don't put a negative exponent. Any questions or concerns there? All right, so what I hope you take from today is that dealing with the limit definition of a derivative definitely takes some work that we don't want to have to go through every single time we deal with functions, especially when functions have more and more terms or things involved. It can definitely become tedious, or to the point that, we'd have to have some creative ways to deal with stuff, right? Remember, we looked at rationalizing the denominator one aspect, okay? These rules are going to help us. So what I wanted to focus on today was, as I said, was the power rule, and then dealing with the derivative of a constant term. These other rules here help us just go through the process of dealing with stuff like 2x, or as we saw here, 2x cubed, right? So that's where pulling a coefficient of a variable term out. The sum and difference allows us to handle things that have multiple terms. Now, as you see here, this is a great way to think of what we're doing. What we're taking when we say we're doing the derivative function, we're taking the derivative of each term because they're separated by addition and subtraction. Now, as I said on this one, I wrote this out in a more expanded form, but if you're comfortable, you don't necessarily need to write out those additional steps. But if it's going to help you, make sure you put what is going to benefit you. If you need to see this, write that out. Now, one thing I want you to say, this does not represent division, right? Remember where we got that from. What we're using that from is that change in y all over a change in x. That is an average rate of change. Through the limit process, we brought it to this situation where it represents an instantaneous rate of change. Here, we're bringing it to the perspective of a function, right? So the y here, the way we say that is the derivative of y with respect to x. So this statement here is us saying the derivative with respect to x of this function. So this is not something you can multiply by dx and everything, right? It's a statement that says we are doing this. Okay, so be careful with that. Now, as you saw here, we can continue by dealing with terms individually, but there are going to be times where we still have to be creative, right? So that I wanted to show this example as a rational that we could simplify so that we can use the power rule, okay? Is there any questions or concerns as we finish up today? All right, so what I would say is just make sure we're working on those. I'll double check to make sure the assignments for the first few sections of dealing with the derivatives is up. Okay, as far as the test is concerned, I hope to have my schedule kind of back into a positive place Monday after we lost last week. So I will make sure to update the schedule Monday or by Wednesday next week. I'll say Wednesday at the latest. Any questions or concerns before we leave, though? All right, then if you don't have any questions, concerns, have a great day and enjoy your weekend. I'll see you on Monday.